Okay, so hello everyone. I'm Yingjun Tian, currently a final year PhD student from University of Manchester, and I'm also from digital manufacturing lab. And my topic is SORO-MADE soft robotic mannequin with programmable shape deformation. And this EPSRC project is a collaboration with Dr. Simon. And I will first start from the motivation. According to public research, clothing is currently a 1.3 trillion US dollar market, with 25% of the clothes never sold, and another 25% sold but never worn. What's worse, it is estimated more than half of the fast fashion product is disposed under a year, which puts pressure on resource, pollutes and degrades the natural environment and its ecosystems, and creates significant negative social impact at local, regional, and even global scales. One reason is that for many people, it can be challenging to find fitting clothes, as standardized size often cannot account for individual difference, such as the longer or shorter arms, asymmetries, body dimensions that fall outside the commercially available range, or even missing extremities. In a word, size to shape cannot account for the need of the most of the population, which can be further illustrated in a recent survey conducted by Dr. Simon. 86 out of 201 participants cannot find fit garments in all 63 brands in the UK. As a result, we ask for made-to-measure garment personalization. Recent year, designers and innovators are searching for biorecyclable materials and a novel garment fabrication method to boost sustainable and made-to-measure garment personalization. For example, Fabricant showcased their spreadable dress in Paris Fashion Week last year to demonstrate the idea of personalized dress with new materials in the left figure. And in the right-hand figure, you can see like Dutch textile designer Anila Hotkin combined textual elements with disc-shaped pieces of mushroom mycelium, which is biodegradable material for products and construction to create sustainable dress to address the issue of mass garment fabric waste and pollution. So considering the requirement for made-to-measure and sustainability in garment industry, we propose to include soft robotic technology to construct many degree-of-freedom deformable mannequin set up to deform to different human body shapes, which can benefit the sustainable and made-to-measure garment personalization for large group of individuals with only limited number of robotic mannequins set up. The mannequin will also be able to operate in the environment with high temperature steam to allow for dripping and forming of garments. This is the first work of my PhD study. It is to build a soft robotic mannequin system to prove the concept. There are 3 challenges to build a soft robotic mannequin with programmable deformation, design, fabrication, and deformation control. In this presentation, I will introduce the recent progress of our SORO-MADE research. And the left-hand side shows the system overview. Our soft robotic mannequin contains several inflatable chambers that consist of a soft material that can be deformed by inflated air, and with its deformation can be accurately captured by 3D scanner. Then the capture shape and the target shape will be compared, and the calculated shape difference will be sent to deformation control algorithm in the right down corner to adjust the actuation, and iteratively, this shape difference will gradually converge to a low level. And for the chamber design, we start by extracting average body shape from the database, then segment the body into several chambers, Then we use free-form modeling software Rhino to design the manufacturable chamber actuator. After fabrication steps at the left-down corner, you can see, and we assemble all the chambers into the base core in the right up corner to form the deformable mannequin. Also, a control system comprised of control software and the pneumatic control hardware is developed to automatically drive soft robotic mannequin to an optimized state and stay for long period so that we can do some measurement and draping of the garment. And the left-hand side shows a multi-threading control software based on Qt for vision acquisition, pneumatic regulation, and algorithm execution. And right-hand side is the pneumatic control hardware, consists of circuit board and inflation modules. This is our QR code. You can scan to for more details. And this is our control box, which is a circuit shown here. And this is a modular design, and we can like add or remove each inflation module separately. We also developed the dual PID controller to regulate the pressure control. So here we show the system running as a whole to fit a given body shape. Because like the two shape difference, their relative position and the pose is very important because so we also include pose registration in the loop to let two shape to actual shape difference can be calculated. And you can see after several rounds of iteration, the deformed shape are very close to the target shape. Here we shows like the color map after the convergency. You can see the average arrow is around 3 millimeters, and the maximum arrow is around 5 to 12. And for my second version of Mannequin, we developed a soft deformable mannequin simulator so that we know our chamber segmentation, how it would deform. So it can guide our segmentation and to refine and improve our design. In the right-hand corner, you can see its deformation ability is quite large, and it is quite similar to the commercially available final element analysis software Abacus. And you can see this is the first version of our deformed mannequin. And then we extend our design region from the front body to the full body. And this is our second version. And now we are under construction. So you can see this is our general simulation framework based on geometry computing. And we assigned some boundary condition so that the simulation can smoothly run. And then we simulate outer membrane deformation by including the collision detection and response. In the future work, because here you can see the design is quite intuitive. We segment the chamber without any consideration of the database. Now, due to we have some data from the CEDAR dataset, so we analyze the database by clustering with some measurements, and we can see here we clustering the body range from UK size 10 to 14, and we selected 100 representative females, and we will future work we will use this kind of big data about real human to guide our mannequin design, including core shape optimization and automatic segmentation. We want data to tell us what is the range of body shapes and which part is most critical and sensitive, so that we can like escape the intuitive design and try and error. Thanks for listening. This is my presentation.